So welcome to this afternoon session on quantum cryptography. We have three wonderful speakers for you. So the first speaker is Aditya Gulati. So take it away.
Hello. Hello, everyone. I'm Aditya Gulati, and I'm going to talk about pseudo-random function-like state generators. This is joint work with Prabhanjan Anand, Ewan Kian, and Henry Ewan. Classically, we know that pseudo-random objects are very important for cryptography and complexity theory. In fact, we use almost all of the cryptographic primitives are built from the plethora of pseudo-random objects that we have. So it's natural to ask if we have something similar in the quantum case. To define pseudo-randomness in the quantum case, we should first see what randomness looks like in the quantum case. It's a little non-trivial to define since the space we have is continuous. But there's this notion called Haar random states, which looks like essentially picking a random point from this continuous space. So with this randomness, with this definition of randomness in mind, we can define pseudo-random quantum states to be efficiently computable states that look like Haar random states. Formally, we need two properties. One, efficient generation. So given a key K, there needs to be an efficient circuit, polysize circuit G, such that given a key K, it produces an n-qubit state. We call this an n-PRS. And we need a pseudo-randomness property from this. It's defined similar to the way we define it classically. So the output of the PRS generator should be computationally indistinguishable from a Haar random state. Though this is not enough for most of the applications. And this is because we can't copy quantum states. So once you do any computation on one of these states, we potentially can lose the state. Hence, we work with a polynomial definition of this, where we are given polynomially many copies of the PRS state and polynomially many copies of the Haar random state, and this should still be computationally indistinguishable. Now that we have a definition, it's natural to ask for constructions. So we know how to construct PRS from one-way functions. This first construction was given by Ji, Liu, and Song in 2018, and then further constructions were given by Brakarsky and Shimley in 2019 and 2020. One of the most studied construction is the binary phase PRS, where we give random phases to each computational basis state, where the phase is chosen by a PRF, a pseudo-random function. So now that we know how to construct PRS from one-way functions, but are one-way functions necessary to construct PRS is an interesting question. Kreshmer answered this in 2020, where he gave an oracle with respect to which one-way functions do not exist, but pseudo-random states still exist. This is very interesting, since this potentially gives us a set of weaker assumptions where we don't even have one-way functions, but we can still construct cryptographic primitives. So in fact, and also another question we get here is, since one-way functions are not necessary, can we construct PRS information theoretically? We know that classically, even one-bit stretches require computational assumptions. But in 2020, Brakarsky and Shimley showed that there exists a C such that C times log lambda length PRS can be constructed information theoretically. In our paper, we show that if the output length is equal to or greater than log lambda, then we can't have information theoretic security. We need some computational assumptions to have this. Now that we know constructions of this, we should ask whether we can construct cryptographic primitives from this. AQY and MY in 2022 showed that we could construct some cryptographic primitives from pseudo-random states. So to do this, AQY defined a primitive called pseudo-random function-like states, which is the analog of pseudo-random functions in the quantum case. And we again require two properties from this. So given a key K and an index X should produce an n-qubit state. And they define security to be, they define selective security for this, where we choose polynomially many queries in the beginning, and polynomially many copies of the output of the PRFS generator on these polynomially many queries should still be indistinguishable from polynomially many copies of polynomially many states sampled from our random distribution. But this is not enough for most applications, because sometimes we need the adversary to be able to choose queries adaptively, that is, choose a query number 2 after querying the function on the first query. Further, sometimes the adversary also gets quantum access to the function. So the adversary can submit a superposition over query states and gets a superposition of answers and result. So a question that can be asked here is, can we construct these stronger notions of adaptive querying and quantum access? So in our paper, we give constructions of adaptive query PRFS from post-quantum one-way functions, and we also give constructions of quantum access adaptive PRFS from quantum one-way functions. We also give a simpler proof of binary phase PRS that we just saw. We had a proof of security from Brukersky and Shimley in 2019, but that was much more involved. We give a better representation of our random states and use this to prove that binary phase PRS is still secure. So coming back to applications from cryptography, we know that in 2022, AQY and MY constructed cryptographic primitives from PRS. But one common property from of these was that they required quantum communication. We expect quantum communication to be a much more expensive resource even when quantum computers become prevalent. So a natural question is quantum communication required whenever we use PRS? In our paper, we construct commitment schemes with computational binding and statistical hiding that only require classical communication. We also give PRS-based quantum one-time part scheme, which only requires classical communication. So on to the techniques. Due to constraint in time, I'll only be covering techniques in the computational assumption section and in the commitment scheme section. The rest of the techniques can be found in the paper, in the full version of the paper. So the statement for computational assumptions is, if G is a log length PRS, then there must exist a distinguisher such that this distinguisher can distinguish with at least probability 1/3. So the first observation here is that G is almost always pure. The output of the PRS is almost always pure. This is because if it is not pure, then the distinguisher can run a swap test to check for purity, and on big enough number of on polynomially many copies of this, it can distinguish with probability 1/3, since our random state is always pure. So once we have this, we prove this by a dimensionality argument. So the dimension of the space spanned by all the PRS outputs is less than 2 to the lambda. This is because there's at most 2 to the lambda number of keys. But for the Haar random state, T copies of a Haar random state span this dimension. This is equal to the dimension of the symmetric subspace on T copies. In particular, when T is said to be lambda plus 1, this is greater than 6 times 2 to the lambda. So we have a natural distinguisher here, which we just project on the space spanned by all the outputs of PRS states. When we project here, PRS always passes this test, but the Haar random states will fail this test with at least 1/3 probability. Hence, we get a distinguishing probability of 1/3. Now, onto the techniques in constructing the commitment scheme. We start with the commitment scheme given by AQY. Here, the commitment phase was a two-message scheme, and then the reveal phase had just one message where Alice sent all the randomness to Bob. One thing to note here is that the quantum communication only happened in the commitment phase. The quantum communication only happened in the commitment phase. So to convert this quantum message to classical, we use techniques used in tomography. Tomography is a procedure where we can get a classical description of a quantum state. In particular, given some copies of a state rho, we get M such that M is still closed in rho in some norm here Frobenius. So notice that the number of copies here needs to be exponential, but since n is log lambda, we get this to still be efficiently computable. Now with this in mind, we can just replace the quantum communication with the output of tomography, which is a classical message. This converts the scheme to just have classical communication, but the adversary can still cheat. This is because we have no way of checking whether adversary actually ran tomography or just outputted a random matrix. To detect this, we build this primitive called verifiable tomography, where we equip tomography with a verify algorithm, which can be used to detect whether the adversary actually ran tomography or not. Hence, to convert the scheme completely now, we replace the quantum message with the output of tomography, and during the reveal phase, Bob runs verify to check whether Alice behaved honestly. And this is how we convert the scheme to just have classical computation. Here's a summary of all that, of all the results that we have in the paper. Thank you.
Thank you very much. Any questions?
Can you tell us a little bit more about the verifiable tomography bit?
So we in fact get a generic scheme to convert any tomography algorithm to equip any tomography algorithm with a verify scheme. There is a natural way to construct this by just running enough number of tomography running tomography enough and then just checking the distance.
Thanks.
Can you once again elaborate what do you mean by verifiable tomography? I mean, what's really the attacker model?
Sorry.
What is, can you briefly elaborate? What is verifiable tomography? I mean, what's the attack model? What is the attacker trying to, what's the bad event?
So so one of the parties knows the channel using which the state is produced, where the channel takes as input some classical string, and then the party needs to check whether in fact the state produced was produced using this channel on the classical string or not. So to verify party number one sends the string that it used on the channel, and then party number two just runs the verify scheme with the classical string and channel information and output of tomography to verify whether it is correct.
I see. Because I was just wondering that you can rerun the protocol again. That can be like a, I mean, verify algorithm.
Essentially, yes.
It's okay. I see. Thank you.
You get a non-interactive commitment, or the commit phase is interactive?
It's a two message.
So the commit phase is also interactive. Yeah.
Yes, two.
Okay.
Two message.
Okay, thank you very much. Let's thank the speaker again. Okay, so next we have a remote talk by Ahmed Reza Rahimi. I hope I said your name reasonably accurately. And take it away.
Okay, so is my screen share fine? Everything fine with that, or?
Yeah.
Perfect. So today I'm going to talk about candidate trapdoor claw-free functions from group actions with applications to quantum protocols. This is a joint work with Navid Alamati and Giulio Malavolta. And in this talk, I'm going to mainly focus on the trapdoor claw-free functions and group actions. So what are these trapdoor claw-free functions? They're functions. So let's talk about trapdoor functions first, which they're functions that are they're functions from a domain X to range Y that are easy to evaluate in one direction and are hard to evaluate in the other direction unless you have the trapdoor. And what is the claw-freeness property? Imagine this function is a 2-to-1 function where the input is separated into two same size input subsets, and the function is going to be separated into two different functions, f0 and f1, which these two functions are bijective functions. And f0 is a function from x0 to the output range, and f1 is a function from x1 to output range. And a claw is referred to as two inputs, x0 and x1, which they are mapped to the same output. And the claw-freeness property suggests that finding a claw should be hard. So what is let's try to expand this property to something stronger, which we say, okay, if finding a claw is hard, what about finding any information about the claw? Which brings us to this other property, which we call it adaptive hardcore bit property. Where adaptive hardcore bit property suggests that basically if you get any like input and their corresponding output, it is hard to find any information about the other pre-image, where this claw-free, it is also guaranteed that the other pre-image also exists. So if I want to be more formal about it, I can say it is hard to find the input X and a vector D. This is a binary vector and it's non-zero, of course, and a bit C such that the inner product of D and the XOR of two pre-images equals to C. So you can compare it to the normal hardcore bit property, where this vector D is actually a constant vector, which is 1 at one position and 0 elsewhere. And then this is going to give you a normal hardcore bit property. But here, this vector D is chosen adaptively, even by the adversary. And we're saying, okay, even if this vector is chosen by the adversary, it is still hard to find any information. Okay, so why do we care about this property? Apparently, finding both a pre-image and an adaptive hardcore bit pair is hard for any quantum polynomial time adversary, which this property of this adaptive hardcore bit enables the trapdoor claw-free functions to have numerous applications in quantum protocols. But these things have been around for a while, and recently there has been so many applications in quantum protocols by these trapdoor claw-free functions. For example, the test of quantumness, certifiable randomness, the classical verification of quantum computation, quantum FHE, proof of quantumness, deniable encryption, and there are so many other applications. So this is an important topic to study. Well, there's also, so we require these TCFs to be post-quantum. And all of these post-quantum TCFs are based on the hardness of the quantum hardness of LWE, which is okay, but unsatisfactory. So there's a natural question that can we get these TCFs from other quantum hard assumption? And this paper answers this question, which is we're getting TCFs from isogeny-based group actions. Okay. So what are group actions? Group actions are some sort of functions that takes a group element and a set element as input, and it maps it to another set element. And there is this variant of group actions, which we call them effective group actions, or EGA for short, where they have this properties where they can be efficiently computed. The action can be efficiently computed. Then, for example, if the group is an additive group, the G plus X action on X, G plus H action on X for G and H in the group is going to have like associativity property, and the identity element of the group mapping maps each set element to itself. So what about hardness assumptions that we can get from these group actions? There's this one-wayness property where it says that given a set element and a group and a random group element action on this set element, no attacker can find the group element. So you can think of it as something similar to discrete log assumption, where in the discrete log setting, this action can be represented by the exponentiation, and the set can be represented by an actual group with the generator X, and the group is ZP star, okay? And then finding, having X and X to the G is hard to find the group, the G, okay? So this one-way EGA doesn't have enough structure to build, to be able, so that it doesn't enable us to build some cryptographic primitives on it. Then we define another assumption, which was defined by Alamati et al., which was called in AsiaCrypt 2020. And this assumption is called linear hidden shift assumption, where it says that having a matrix of group elements, a vector of set elements, and a binary vector V, which is here our secret vector, an MV action on X, you can think of this MV as some sort of a subset sum. And this tuple should be computationally indistinguishable from a tuple with X, M, and some random set elements. So at the first glance, it reminds you of LWE, where there is action, but there's no noise in this setting. And the reason that it still remains hard is that once you compute, you compute an action, you're in the set. And in set, you do not assume that you have any structure. You cannot perform any operation. So the components of this MV action on X cannot be combined. And this is important because intuitively, it doesn't allow you to have some sort of Shor's-like algorithms on the LHS assumption. Okay, now that we have our assumption, let's try to create a simple claw-free function from our assumption. And this function, let's assume that b is a large integer, and the domain of the function is 0, 1 times b to the n to some set x to the n. So what are the public parameters? It's basically the challenge from LHS assumption and the evaluation of the function on some bit and on some bit b and set and vector s in the domain is going to be m times s plus b dot v action on x, where if b equals 0, so this b is actually getting the index of the function. If b equals 0, then you can compute the ms, since you have s and m. And if b equals 1, since you have mv as well, you can compute it. Okay. What about the claw-freeness property? So the claw-freeness property says that you can finding a claw breaks the LHS assumption. Okay, so how can you break the LHS assumption? You can find the difference between S0 and S1 in V, and then break the LHS assumption. And then break the shift vector of the LHS assumption. So there's a problem with this function. There's no trapdoor. Okay, and also it is hard to argue the adaptive hardcore bit property of this function, where we can deal with these issues of the no trapdoor issue, which can be resolved by some sort of other assumption, which is called the extended LHS assumption, which is a stronger assumption than the LHS. And for adaptive hardcore bit proof, we define a new notion called direct product adaptive hardcore bit, which we get to it in the next slide. So let's remind ourselves what was the adaptive hardcore bit. Adaptive hardcore bit said that finding a pre-image and an arbitrary non-zero binary vector and any information about the other pre-image is hard, but for any QPT adversary. Okay, and in the paper by Berkersky et al., they said that there exists some efficient transformation that can translate like this normal adaptive hardcore bit tuple to some other tuple of like D and some of vector D and D prime, and the inner product of this D prime with the shift vector. You can think of this shift vector as the input of the function with the public parameters. With these public parameters, what does it say? It says that adaptive hardcore bit property is essentially the same as finding any non-trivial parity of the shift vector. We can emphasize that this transformation is not a generic transformation. However, this is something specific to their construction, and the this is something specific to their construction, but we can also translate it to our construction as well. So what is this direct product adaptive hardcore bit property? It says that for any QPT adversary A, given n independent public parameters, as well as their evaluation on some shift vectors, some different random shift vectors v1 to vn, it is hard to simultaneously find this non-trivial parity of shift vectors for all of these vectors v1 to vn. Okay, so we are going to find this d1 and the inner products for all of the vectors, and let's compare it to the normal adaptive hardcore bit property that we had. In the normal game, we get the same thing, the adversary gets the same thing, but it argues that the hardness is, it's hard to find the XOR of all of the inner products. So here the advantage of the adversary is something negligible, and here it's negligibly close to 1/2. And there's a conjecture that we leave it as an open problem, which is independent of knowing anything from group action and stuff like that. And the conjecture is that, does this direct product adaptive hardcore bit property implies the adaptive hardcore bit property or not? Okay. So the function, so now the main part of the paper is to create a function family that satisfies this direct product adaptive hardcore bit property. For that, we need to define the correlated pseudorandomness first. We say that the function family satisfies this correlated pseudorandomness if you have the tuple considering containing n independent public parameters, and the evaluation of this function on these public parameters, as well as a same input vector w, it should be indistinguishable, computationally indistinguishable from the tuple of public parameters and some uniform elements in the range of the function. So now let's define this procedure P, which we call it like efficient procedure P, that takes the correlated pseudorandom tuple of a function over same input w, as well as n uniform binary vectors. And what it outputs is it somehow gets these binary vectors in the input of the function with different public parameters. And the important part here is that this thing should be statistically indistinguishable from a tuple of n public parameters and the evaluation of f on those public parameters and some, let's say, binary vectors, which we call it shift vector here. Okay, and there's this theorem that we have in the paper that says, we say, okay, if f is a function family that satisfies this correlated pseudorandomness, and there's a corresponding procedure P for f, then it satisfies a direct product adaptive hardcore bit property. And we can have our results as in this paper are as follows. We construct a trapdoor claw-free function family and this procedure P. Finding this procedure P is the main part of the paper, actually. And we create this trapdoor claw-free function family and the procedure P from extended LHS assumption. And later we use our TCF to have a quantum protocol for qubit test. Thanks.
Thank you very much. So we have time for one quick question while the next speaker is setting up. Anybody? I have a quick question. So, okay, sorry, this is one of the back. Okay, great.
So I wanted to ask, like, if the functions are like set elements and your message space is like group element, what is the problem to get like what is the can you get a claw-free function just by applying the group element on the set elements, or can you not?
What do you mean by applying?
So if functions, so if you have f0 and f1, right? So suppose you consider two set elements, x0 as f0 and x1 as f1, and now your message, say a group element g. So f0 of g is g star x0 or g star x1. So in that case, you would get a trapdoor function, right? Given the discrete log of x0, x1, you can invert, and the claw, given a claw, you can find the discrete log. So why doesn't that work?
You can have that, but the problem is adaptive hardcore bit property. How would you argue the adaptive hardcore bit property with this construction?
I see. Okay, you need that.
I think if I get it correctly, it is the same construction of the hash function. I mean, you can tweak it, the hash function that they had in the
in ADP, yeah.
Yes, exactly. In the hash function in that paper is what you're referring to, but arguing the adaptive hardware bit property is pretty hard for that. I mean, we don't know how to do that.
Okay. Okay. Thank you.
Thanks. Let's thank the speaker again. So next up we have Jiahui Liu.
Okay. Don't press the button. Okay. Okay, cool. Hi, everyone. I'm Jiahui. I'm going to talk about collusion-resistant copy protection for watermarkable functionalities. This is joint work with Qipeng Liu, Lowen Chen, and Mark Gendry. As we know, there is a famous theorem in quantum information that says, given an arbitrary unknown quantum state, there's no general procedure to turn it into two copies same as the original one. And this theorem has inspired some of the classically impossible cryptography constructions. For example, the famous quantum key distribution protocol, the quantum money scheme, which says a bank can issue banknotes and unclonable quantum states, and the users cannot double spend because of no cloning. And then there's this extension, which we will focus today, of quantum money called quantum copy protection. And some of the more specific extensions of quantum copy protection are like signature tokens, which are a specific type of one-time signature, and unclonable encryption and decryption. And there are many more. So what is quantum copy protection? Quantum copy protection is a way to encode a classical functionality into a quantum state. So imagine there's a software vendor who wants to sell a software it designed, and it doesn't want the users to pirate and make and sell the pirate copies. Of course, the company would probably go broke. So what it does is that it can first we can view this software just as a classical functionality, right? And then there's a procedure that the software vendor turns this classical functionality into a quantum state, and then it sells this quantum state to a user. And when the user receives it, and it can just run this quantum state on any input it wants, and it would get the same. It would get the same result as if it is running the original function f. However, what the user is not able to do that if it wants to make pirate copies of the program, what it cannot do is that it cannot produce two programs, P1 and P2, and these two programs would compute the same functionality as the original function, copy protected. And I will just make a very quick detour to something called watermarking. So of course, classical cryptographers, they also care about copy protection and copyright. And but the thing is, classical information is always copyable, right? So if you just receive a piece of information, even if it's obfuscated or something, you can just always copy the entire thing. But still, we can do something about it. One thing is called watermarking. Basically, you embed a watermark into a function. And if the pirates, they want to remove this watermark, they have to destroy the underlying functionality. And we've seen a lot of constructions for watermarkable functionalities, but they are mainly just cryptographic functions, such as a decryption function in a public key encryption scheme, a pseudorandom function, or a signatures, as well as extensions that's built on these cryptography functions. And we will soon see that there is actually an interesting connection between watermarking and copy protection, even though one of them is quantum and the other is classical. So let's take a quick look at some previous results. So in this talk, I will mostly focus on these three primitives, copy protecting decryption, which we will call unclonable decryption for short, copy protecting PRFs, and copy protecting assigning algorithm in a signature scheme. And these were previously built, firstly, they were built relative to oracles, or we say like virtual black box obfuscation of classical circuits. Of course, that's a very strong model, and we don't want that. And next, we had works that build them from in the plain model from I/O and one-way functions. And in the same work that first brought up these oracle constructions, they also observed that for all the watermarkable functions, as we mentioned in the last slide, and also they are actually mainly they are the functions I listed here. There's like a black box way of lifting them from using watermarking together with quantum money to leave them to be copy protected in a weaker copy protection security. But that is indeed a much weaker security than the copy protection I just talked about. And the question is whether we can actually copy protect all the watermarkable functions with the standard security notion. So for this talk, I will for simplicity, also because of restriction on time, I will just focus on one specific type of copy protection. That's the copy protection for decryption keys in a public key encryption scheme. And this notation is for something we call 1-to-2 security. There's a keygen algorithm. It outputs a public key and decryption key pair. The public key is classical and decryption key is quantum. And then there's an encryption algorithm. It takes in the public key a message and outputs a ciphertext. That's all classical. And finally, the decryption procedure is quantum. It takes in the quantum decryption key, a ciphertext, and outputs the message. And what you want, of course, is that, okay, if I give the user the public key and one copy of the decryption key, it's not able to produce two states here, row 1 and row 2. And when I ask these two states to decrypt, they can simultaneously decrypt successfully for me. And we don't want that to happen. But indeed, in the last slide, we see here we only talk about we give one copy to the user. And in this past works, the security for this 1-to-2 situation was shown. But what they did not consider is that in the real world, we do not just give out one copy to the user, right? So when a software wants to, a software vendor wants to sell some of the copies, it might sell like polynomially many of them. And these users who receive these copies, they could somehow come together and they just work as one malicious user that tries to generate one additional copy from all the polynomially many copies it already possessed. So in our paper, we would consider this collusion resistance notion is that the adversary cannot generate one additional copy even if we give them k polynomially many copies. And here, for simplicity, we illustrated it as giving two copies, and it cannot generate three. And as we mentioned, all the previous works, they are not collusion resistant. And in our work, the first thing we do is that we also construct copy protection for a standard existential unforgeable signature scheme that's not done in the previous work in the plain model. And we made all of them collusion resistant. And we partially answered the question that we were actually able to copy protect the major watermarkable functionalities, even though it's still not that ideal because it's not a black box lifting from watermarking to copy protection. So I will briefly go over the syntax for 223, which is a simplification. Of course, we actually consider k to k plus 1. So in the keygen algorithm, we actually generate two public key and decryption key pairs, and they are independently sampled. And the next, and in the encryption scheme, here I'm writing it as a simplification. You can see it as the encryption scheme takes both of these public keys and it generates two ciphertexts of the same message, and each encrypted under one of these public keys. And the decryption algorithm here sorry, the notation might be a little confusing. The decryption algorithm actually takes one of these decryption keys to do the decryption, because as long as it possesses one of these keys, it's able to decrypt one of these ciphertexts above, and then it can obtain the message. And what we don't want is that it can generate one additional key from these two keys given. And on the high level, the idea may be very simple, because here I said we have two pairs of keys. Okay, if the adversary is able to generate one more, then we may do something like a reduction to a 1-to-2 security, where we just use a pigeonhole principle classically, because if it's able to decrypt, then there must be two keys decrypting the same message under that's encrypted under the same public key. But the idea is not actually working in the quantum setting, because the adversary could do something weird. It could entangle these three keys in a weird way that if you just directly grab two keys and try to do the reduction, it won't work. The thing is that you actually have to show that we can do something similar to a pigeonhole principle in the quantum world, that we need a procedure to measure which ciphertext each key uses to decrypt in order to get the message, so that we can actually grab these two keys that decrypts the same message to break the 1-to-2 security. And this is a very high level description of what we do. Is that we perform a sequential measurements in a thought experiment first. So we start with here the quantum key is actually a pirate key, not the original key. And we start with a first distribution where we just do something the same as the original security game. We just feed the quantum key with these honestly prepared ciphertext, and we test. And there's a quantum measurement procedure that tests the success probability of this pirate quantum key. Okay, suppose the adversary is a successful one, then of course it should decrypt with a large probability for this first distribution. Okay, then what we do is that in the next sort of a hybrid game, we turn off the first ciphertext, we replace it with a dummy ciphertext, and we say, okay, are you still able to decrypt? And we do that until we replace all the ciphertext with dummy ciphertext. And it's easy to see that somewhere in these hybrid games, there must be a gap somewhere in between. You must be able to find that after you turn off one of these ciphertexts, turn it into a dummy one, then the adversary stops being successful. Its advantage becomes negligible at some point. And what we do is that in the real game, we do these sequential measurements and stop before this ciphertext. Before this ciphertext, it has this large jump in success probability, and we use this key to extract and do the reduction. And there is, of course, more subtlety to handle, and I will not go into those details. And please refer to our paper if you're interested. And okay, finally, there are some open problems. For example, here you might already see that we actually have a bounded polynomial many keys, because our keygen algorithm depends on the number of keys we have to issue. So what about unbounded one? Like the keygen doesn't depend on it at all, and you don't have to know how many users you have before you issue out the keys. And there's some other direction. For example, here we can do collusion resistant copy protection for these watermarkable functions. But what about more functions? Is there like a general way to, for example, leave to the previous construction for all unlearnable functions into a collusion resistant one? And that's everything. Thank you.
Thanks. Any questions?
Do you know any barriers to constructing these things from sort of more standard or sort of weaker assumptions? Do these things actually imply quantum money, for example?
Yes. quantum
that's a
copy,
barrier.
yes, quantum copy protection for the decryption key quantum copy protection for decryption key of a public key encryption scheme implies quantum.
Okay, so that's sort of a barrier.
So yeah, that's sort of that.
So maybe a bit of a naive question. I'm not that familiar with this, but in the attack model, does the adversary have to generate a reusable key? So suppose the adversary generates a key that works only once, then this would not be secure against that.
Oh, that's actually a great question. So the adversary could generate a key that only works once, but the measurement we do is actually the measurement procedure that we do to measure the adversary's success probability actually avoids that issue. So like we don't have to, we're sort of doing like an in-place amplification of the adversary's success probability. And even if it's only has some weird property that it would destroy, self-destruct after one time, we would still be able to find out. Right.
Sure, thank you.
Great. So let's thank Jiahui and all the speakers again. And there was a coffee break, I think.